Thank you, Adam, for the invitation. I'm a senior research scientist in the building systems group at Epic Innovations in Canada, and also a member of ISO the TC 169 Timber Structural Committee, and a member of the Wood Structural Committees of Canadian Society for Civil Engineering, and a member of the Technical Task Group of the Canadian Standard for the Engineer Design in Wood CSOD6. So I conduct research by testing, modeling, or both to investigate the seismic performance and the fire resistance of timber structures to support the code and standard implementation of timber systems. And meanwhile, I'm also an external graduate faculty, similar to a John professor at the University of Maine in the US. So I co-supervise graduate students there. And I also have some cooperation with the Canadian University. So I also advise master and PhD students at the UBC, McGill University, and also Universities of the Waterloo. So my special expertise lies in the advanced and practical numerical modeling of timber structures under different actions like the seismic, wind, fire, moisture, and also the time effect. So this is basically who I am and also what I do.
Amazing. Well, can you start maybe just by telling us a little bit about the differences when you're modeling and looking at timber and how it might be different to concrete and steel?
This is a good question. The main difference among these three material and structures lie in two levels. The first level is material level. As we know that steel actually is an isotropic material, and reinforced concrete actually is a composite material, and timber is an orthotropic materials. So modeling of timbers at the material level is more complex. And the timber actually have the different elastic properties and strengths in different wood grain directions. And even though in the same wood grain directions, the strengths and also the failure mechanism of timber will be different. For example, under tension, it will fail brittlely. Under compression, it will yield ductily, in a ductile way. So that's usually we need to have a zero Bolden constitutive model to simulate the timber correctly. Another level is the system level, because different every material have their unique mechanical characteristics. So different kind of the design philosophy or strategies will be applied to the design of different structure systems to optimize the use of material. So the structural behaviors and also the modeling emphasis for different structure systems will be different. Here I want to share the two examples. The first one is the shear wall systems. Concrete shear wall system actually is governed by the cracking of concrete and also the yielding of the rebars. And the system is usually simulated with the beam column elements with the fractured plastic at the bottom. But for the timber shear walls, usually then the behavior is governed by the connections at the bottom and also between the panels. And so we usually simulate the panel with the shell element and the spring element for the connections. This is the difference between the concrete and the timbers for the shear wall system. The second example I want to share is the base frame system. For the steel base frame systems, it's governed by the diagonal braces, which is actually will yield under tension, buckle under compression. So when we model the timber for the steel base frames, we need to pay attention to the model of the diagonal braces. But for the timber structures, the timber base frame system actually is governed by the end connections of the diagonal braces, not the diagonal braces. So for the timber base frame, we need to pay attention to the modeling of the end connections to make sure that we select the shear Bolden his model to represent the behaviors of the timber connections. So this is how how we see the difference among timber, steel, and concrete structures in terms of the modeling emphasis.
That's an incredibly dense and awesome, enlightening answer there. And so, can you start by introducing the modeling guide briefly? And I'd just like to say that, I mean, it's, and because you're a humble man, but it's a 740-page document, and I know some people in Australia who have been part of it, and I think you've been able to get the world's best engineers on this topic come together and collaborate for a beast of a document that is taking the industry forward. So, firstly, thank you on behalf of the world for putting that together, and secondly, over to you and talking about what this guide is.
Thank you, Adam. And also, I'm very happy to share the honor and share this guide with you guys. I think we can go back to several years ago. I think we conducted a survey, and then we found out that most of the engineers, they are familiar with the modeling of the steel and concrete structures, but they are not familiar with the timber structures, especially mass timber structures. And nowadays, the timber structures increasingly require the demonstration of the performance and equivalence of them. And no matter if they are designed following the prescriptive or performance-based procedures. And so that's why there's a huge need for developing this modeling guide. And so at the beginning of 2020, we initiated this global cooperation. We invite more than 100 experts on different areas to work together to generate this guide. And this guide actually have the 10 chapters. Basically, we can divide into 3 main sections: introduction, modeling, and analysis. In the introduction section, we briefly introduce the scope and also the structure of the guide, and also we point out the difference among the timber, steel, concrete structures in terms of the structural behaviors and also the modeling emphasis. For the modeling section, we talk about how to properly model timber structures at different levels, at the components level, connection, assembly, and the whole system level. And also we provide specific modeling consideration for the audience. In the third section, analysis, we talk about how to analyze timber structures under different scenarios and actions. For example, we have the pole collapse and also the wind-induced response, and also the seismic response analysis. And this publication actually is the first of its kind in the world, and also it brings together the experience obtained from the most recently finished timber projects, and also the latest developments of the modeling in timber structures. So it provides a lot of the advanced and practical contents shared by the experts from the academic area and also the engineer area.
So what are some of the load resisting systems that are available for engineers when designing timber buildings?
Oh, that's a good question. Load resisting systems actually is the structures that takes and transfer the load or force to the ground, to the earth. And usually we have there's two main types of the structural systems. One is the gravity load resisting systems. Another one is the lateral load resisting systems. In terms of the gravity load resistance, which actually it takes and transfers the gravity load from the top to the bottom, eventually to the foundation. For timber structures, usually we have the post and beam to transfer the gravity loads. In terms of the lateral load resistance, which actually transfer the wind and seismic loads to the earth. For timber structures, we have the several systems. We have the platform time and balloon time shear wall systems, and the brace timber frames, and the moment resisting frames. Most advanced one include the post-tension shear wall system and also post-tension moment frame systems, which are called press system, which have been invented in New Zealand. Sometimes the gravity load systems and the lateral system would be separated in the building. So one part just take the gravity load another part would take the lateral load. But sometimes the same structure would play both rules to take the gravity load and lateral load. So it depends on the design.
That's great. So you mentioned one thing was seismic, and that's obviously a very important topic. And I believe around the world, there's new building codes that are upgrading to pay better attention to seismic. And it's commonly said that timber is good in seismic regions. So maybe can you tell us how does timber perform in seismic locations, and how should we be modeling to adequately show the performance of timber in seismic locations?
Yeah, most of the area we have a lot of the residents and people and actually in our area have high seismic zone. So it's very important in a topic. And when the earthquake comes, the ground motion will shake the building, and the building have to dissipate the energy by either failure or collapse, or the energy dissipators. And timber structures have been usually be designed smartly, following the capacity-based design methodologies, in which the timber connection would be designed as the energy dissipators to dissipate the energy from earthquake. And other part, for example, the timber part would be capacity protected without any failure. So the timber connection will play a key role in the seismic performance of timber structures. So we need to model them correctly and properly. And timber structure, timber connections actually are kind of different from the concrete and steel connections, because they have the stiffness and strength, electration, and also pinch effect, which are unique to the timber connections. So we need to select the most suitable his-loop model to simulate the behavior of the timber connections. So this is something that we need. This is the major consideration we should put on the modeling of timber structures in terms of the seismic response analysis.
Gotcha. So is that for timber connections, and is steel in timber connections? How does the steel perform, and is that like better performing than concrete structures in your opinion?
I think different connections have the different behaviors. But for example, timber structure for the steel connection, it behave full his-loop. And for the timber structures, the first load would be full, but later on will have pinch effect and decrease a little bit. So in terms of the deformation, I think the timber connection perform very well as well. So yeah.
Good to know. Great. Yeah. So, and about disproportionate collapse, I mean, that's something else that it's, I guess it's got different focus in different parts of the world, it seems, where some places it highlights it in a very big way, and in other places, maybe not as much. So yeah, what is disproportionate collapse, and how should we approach that?
This disproportionate collapse, also known as the progressive collapse, which is a phenomenon in the building when a local damages happen. For example, failure or removal of load-bearing element, and then it causes the partial or entire collapse of the building. And usually we need to deal. This is a new topic then for timber structures. And if we want to prevent this kind of the collapse, we would like to increase the robustness of the system. And there's usually have 6 main methodologies for design analysis and also strategies to improve the robustness of timber structures. The first one is the high force design approaches. Here we don't simulate the progress collapse explicitly, but we will put a lot of the requirements for the design and make sure that the building will not collapse during this time of the event. The second one is the alternative low passing design methodologies with static analysis method. This is the most common and the popular one to investigate the robustness of the timber structures and also other buildings. We have the linear, non-linear, and pushover analysis without consider the dynamic response. The third one is the alternative low passes methodology. but with the dynamic analysis. The fourth one is the key elements. Here we decide the load bearing elements as the key elements. So we would make sure that it has enough resistance to carry the specific prescribed hazard loading and survive from that event. The fifth one is the redundancy approaches. So in this approach, we try to have more low carrying element to share the force. So when one fail, they still have the second or third one to transfer the loads. So this is how the redundancy approaches apply to the timber structures. The sixth one is the compartmentalization approaches. Here we divide the buildings into several sections, and each section actually have their own robustness. So it will be robust enough to prevent the pole collapse. So basically, then there's six widen for the design analysis and also strategies to improve the robustness of the structures.
Great. So it's an incredible piece of work you've put together. It's taken us forward. What are the next steps on this topic?
The modeling guide actually is a great success, and it provides guidance on the modeling and analysis of timber structures. But at the same time, we talk to the engineer and researchers, and we hear that we need more. For example, we need the input data for the modeling, design, and analysis of timber structures. And also, we heard that now we are learning how to do the modeling. It would be great to have the code or standard to make sure that we do it in a standard way to make sure that the analysis result is reliable. So for the next step, I think we will have the two things can be done. One is to develop a database to support the design, modeling, and analysis of timber structures. And last one is the standardization of the modeling of timber structures.
Great. As we're wrapping it up now, Zhiyong, if we look into the future for you, what gets you excited by the future of the industry and where everything's going? So it's an open question, and just in general, what is getting you excited by the future?
I think now we are moving to areas with the computer and simulation and modeling, and also we have the performance-based design methodologies. In the future, we are not going to design the building for the prescription code. We are going to evaluate the building by performance criteria. So in that cases, actually, we need the computer to help us to evaluate the performance, to demonstrate their performance under different scenarios, like seismic, wind, progress collapse, and also other kind of the fire events, to make sure that we build the buildings economically, but also provide the same safety level. And design thing will make us to a digitalization the areas. So we build digital twins, not just show the people how we build it, not just show people how we construct it, but also we show the people how we perform in a way safely to make us confident to have this kind of building built in such a way.
Yeah, well, it's a beautiful future, and it's been great to speak to you today. If people want to find out more about yourself or the modeling guide, where should people go?
Yeah, if you want to, so what's the question again? Sorry about that.
If people want to download the guide or learn more about this topic, where should they go online?
Okay, thank you. If you or also audience want to read more about the modeling guide, know more about this, you are welcome to visit FP Innovations website. It's be web.fpinnovation.ca/modeling. Yeah, or you can send me an email. Is that if you cannot get the right address?
Yeah.
You can send me email by to me at zhiyong.chen@fpinnovations.ca. So yeah.
Yeah, that's awesome. Just out of curiosity, how many people work at FP Innovations? And the reason I ask is, like, you come up with some massive documents, like the very good literature you come up with. So how many people work at FP Innovations? Do you know off the top of your head?
We have roughly to 400 people.
Ah,
But Epic Notion actually is a non-profit company institution. Actually, we do researches actually for the cycle of the wood from the gene
yeah,
to plant the trees and cut the trees, ship to the manufacturers, and then to make the products and ship it to the construction site, and then for the whole implementation. Our group actually is the building system group at the end
yeah,
of the cycle. Um,
okay,
we have experts on different areas.
yeah,
So we have to be people on the seismic, wind, fire, acoustic, vibration, and also energies. So we have expertise on these different areas, and at the same time we will be we are kind of the like to have a close cooperation with the people around Canada, North America, and also the world. So we would like to work together to generate something with high impact. So take the example of the modeling guy. We have we have experts from the applications, but we also have the experts around the world. No matter is a professor or engineers, and whenever they would like to share the knowledge and share the experience, we would love to collaborate with them and then to generate something that have high impact. And so yeah, I hope this will answer your question.
yeah, it absolutely does. It's a beautiful note to end on. Well, thanks so much for coming on the podcast. That was super enlightening and entertaining. So thank you, Zhiyong.